Hi everyone, I'm Anish and welcome to PrepFusion. So today we'll be starting the lecture 7 of root locus chapter, right? So basically we're doing the continued version of our complementary root locus. So in the previous lecture we studied like what is a complementary root locus, right? And like what is the condition for that? Basically when my key is greater than 0 and I have a positive feedback, then we have to solve using the complementary root locus, which is nothing different, just the few of the rules are changed because my angle condition has changed, right? It has changed to 360 degrees or 0 degrees instead of 180 degrees, right? So yeah, we will continue with few more examples in this lecture, and then I will tell you a bit more about the other few cases, right? Case 2 where my k is negative. Okay, so let's start with this question. So this question has asked us to plot the root locus diagram of the following OLTF where we have a positive feedback, right? Do take note, like in the question in the gate exam, they may not tell that this is a complementary root locus. You have to yourself identify whether this is a complementary root locus question or this is a normal root locus question, right? So it is very important to identify that. So you have to understand by yourself, as like here, right? Okay, I should have written also that k is positive. Okay, so I will write like the question will be incomplete without that k is positive. So if my k is positive and I have a positive feedback, then I will follow the rule of complementary root locus and not the normal root locus. So I will solve this quickly, right? So what is step 1? Step 1 was to find my open loop zeros and open loop poles. So what are my open loop zeros? I don't have any, right? None. I have none. Okay, there aren't any open loop zeros. So what about my open loop poles? So open loop poles are like in very well mannered factored manner. So what are my open loop poles? My open loop poles, right, are -1, -2, -3 and -4. Okay, so these are my open loop poles basically. So how many number of poles I have? I have 4 poles and no zeros, right? I have 4 poles and no zeros. Okay, so I have 4 poles and no zeros. So like how many number of branches do I have? That won't change, right? That thing won't change. So branches is equals to number of poles itself. As always, number of poles will be more than number of zeros, so it will be 4, right? Branches will be 4, right? So now how many number of virtual zeros do I have? How many number of virtual zeros do I have? Number of virtual zeros is 4 itself, right? Because that is basically p minus z and I don't have any zeros, right? So number of virtual zeros will be 4 itself. Something has to terminate, right? Like at k equals to infinity, my root locus has to terminate. So it has to terminate to 4 points basically. For that it needs 4 zeros. I don't have those zeros, so they will be called virtual zeros, or you can say they will be called my asymptotes, right? So number of p minus z equals to 4, right? Equals to 4. So these are my basically like the location of open loop poles and zeros. So let me mark the location of open loop poles and zeros, and I will simultaneously do the step 2 also. What is the step 2? Step 2 is finding the where does my test point is located in the real axis, right? Where is my valid point in the root locus in the real axis? So this is j omega and this is sigma. So this is j omega and this is sigma. Then what do we have? We have here -4, -3, -2, -1. Okay, so like let's check what are my valid points and what aren't my valid points. So these are my open loop poles basically. So what do I have to see now? I have to see that on the right hand side of my test point are there even number of poles or zeros, right? Summation of those are even. Okay, if I check here, right, if I have a test point here, what I see, I have 1 2 3 4 poles. Okay, so any point I take in this region, right, it will always be a valid point on the root locus, right? So this point, right, will lie on the root locus. Okay, this is a valid point. Now if I put a test point here, I have odd number of roots here, right? So this point, right, these points are not a valid point in the root locus, right? So this region is invalid. Okay, so this region is valid, this region is invalid. Again, right, if I put a test point here, yes, here, then what do I see? On the right hand side, I will always have two roots on my on the right hand side of the test point, right? So this region, right, is a valid point on the root locus. Okay, so this will be valid. Now what about this? This isn't, right, this isn't, because I will have always one pole on the right hand side of my S pen, right? So sorry, on the right hand side of my test point, so this won't be valid point. Again, if I check here, I have 0 roots on the right hand side of my test point. So again, this is a valid, right? It can be the 0 or even. Already told you, right, it can be the 0 or even. So this is also a valid point, right? So this will be also a valid point. Basically this question was taken from the normal, where we did a normal one. So if you just check from there, right, if you just go and see there, then what you will see is basically this is the complementary of this one. Okay, complementary of this one. So like here, there, these regions were my valid regions, and here these regions are my valid, basically the complementary, right? So what does my test point like? So my test point basically belongs to from minus 1 to positive infinity. So I will go from left to right. So I will write from minus infinity to minus 4, right? Then union from minus 3 to minus 2, then union from minus 1 to plus infinity. Okay, then from minus 1 to plus infinity, basically. So yeah, this is my where does my test point lie, right? This is where my test point lies. Okay, so now let's solve for another things. So as you know, right, we'll have 4 asymptotes. Now let's find out those 4 asymptotes, basically the angle of asymptotes. So what will my theta asymptote? This time, right, the theta asymptote, the formula will change. It will be 360k p minus z, where this k is going from 0, 1, and p minus z minus 1. Okay, p minus z minus 1. So it is going like this one, right? So now, like, I will have 4, right? 4. So it will be 0 degree first, like on the positive real axis itself. That we can understand from here itself, right? So here itself, like, this is always a point on the root locus. So if I will go towards positive infinity, so yeah, this is 0 degree, right? So this is one of the asymptote, this is another asymptote, and other will be like this. Okay, let's see. So if I put k equals to 1, like p minus z is 4 itself, right? P minus z is 4, right? P is 4 and z is 0. So this is 90, k equals to 1, k equals to 2 is basically 180, right? And k equals to 3 is again, like, okay, what do you get? K equals 3 is 278. Yeah, k equals 3 is 278 because 19 to 3 is 270. So this is what we get basically. So as I can see, right, here I have one of the asymptote, here I have one of the asymptote, here I have one of the asymptote, and here I have one of the asymptote, right? So I have 4 asymptotes. Now let's do the centroid, because here, right, my asymptotes are not just lying on the real axis, they are also lying on the complex conjugate plane also, complex plane also. Okay, so the centroid, right, value of centroid will be same as that of the normal root locus. The location of the centroid will be same, the intersection of my asymptotes will be same as that of my normal root locus. Just check, right, just check with the that example that I already solved. So sigma c will be simply minus 1 minus 2 minus 3 minus 4 plus summation of the real parts of the roots poles plus no, I have no zeros, so for no zeros I put 0, then 4 minus 0, which is equals to minus 2.5 itself, minus 2.5 itself, right? So this is my centroid basically. Okay, so let me first like draw it, then you will understand. So I will take this one, so basically, right, this is a valid root locus point, right, and this is a valid root locus point. Okay, and this is also a valid root locus point. And what else is happening? What else is happening is that this is a valid root locus point. Okay, like this is the basically known as the asymptote. Okay, I don't know the breakaway point yet, but what I know is like this is one of the asymptote, right? And this is the other asymptote. I don't know about the complex planes yet. And this is the another asymptote, right? This is another asymptote, and this is also another asymptote. Okay, so all of these are asymptote, right? All of these are asymptote, and the centroid of those are between here, right? Here. Centroid is at minus right? Centroid is at minus 215. Okay, so this is my centroid basically. So what is my step 4? Step 4 is break in point or break away point, right? So this is my step 4. So the solution I will get same as I explained earlier, right? But the correct solution will be another. The points that I will choose will be reverse, basically will be opposite of what I choose on that case. So let's see, right? So like here, right, what is important is that like I'm calculating between two poles. Okay, then what will I get? Will I get break in point or break away point? I will get break away point, right? Because they will start from here, right, and then they will diverge. Okay, they will break up. So I will get break away point. Okay, so if I get break away point, then what will happen? Basically, right, I will to solve that characteristic equation, that is so I will write here no break away, no break in point. I will get break away point. Okay, right, so this one with color red. Okay, so this one is this one. So now right now basically what we should do is like write the characteristic equation. It was basically this time, right? I haven't wrote it down yet, so this should be minus, right? I hope you understand why this is minus. Basically the characteristic equation will be minus s plus 1 s plus 2 into s plus 3 into s plus 4, okay, equals to 0. So from here, like I will just write the solutions. Okay, solutions still will be same. Like basically my a of s will be 1 and my b of s will be this, right? B of s will be this. Okay, now to not waste much of a time, if you just check, right, the solution will be same. The solution of my s will be same, right? They will not change. Okay, from what I found out from previous solution, right? Basically the solution of this equation, a dash of s into b of s minus a of s into b dash of s equals to 0, that will still remain same, right? That will still remain same. Okay, but what will differ? Because the real axis points are changed, right? Or the points which lie on my real axis has changed. So what will happen? The points that I will pick, right, that will also change. The break points that I will pick, that will also change. So basically previously, I hope you recall, I have already written down the solutions. It is my like I will get three solutions. It will be cubic equation. I will get one of them as minus 1.35, another one as minus 2.5, and another one as SB3 as minus 3.618. So I will get three solutions. Now if I get three solutions, which ones should I pick, right? So there I picked 2. If you remember, there I picked 2. Here what I will pick? So first, right, I will copy this range, and this is the valid range, right, where my test point will lie on the root locus, right? Will lie on the root locus. So these points, right, so satisfy this following test point, right? Okay, so first one is showing minus 1.35. so minus 1.35, is it lying in this root locus? No, right? It is not. So it is gone. Okay, now this minus 2.5, is it lying on the root locus? Yes, it is, right? It is basically the centroid also, but here I can see it is lying on the root locus. So minus 2.5 will be a valid point on the root locus. Okay, minus 2.5 will be a valid point on the root locus. Now minus 3.618, will it lie on the root locus? Here, right, it doesn't. Here also it doesn't. So this is between these two, and it doesn't lie in this test point, right? So hence this also doesn't lie on my root locus. Okay, so I hope you understand. I picked the middle one, which I rejected there because that wasn't lying there on the root locus, but here it is, right? So complementary is the basically complement of this, right? So like if you solve this, right, if you solve this, even you want to get a further validation, you will see that I am getting k as negative, k as minus 1, which is not possible. Okay, which is not possible because k will be positive always, and here also I will get k as minus, which is again not possible. But here I will get my k as point 5625. Okay, as 0.5625. I will get my k as 0.5625. So like the solutions will remain same. Solution of this equation will remain same, right? But the points which I will pick will now flip, right? Will change. Basically the points that I rejected there is getting accepted. So you might say the person that I rejected, now another person is getting accepted. Okay, so not that great analogy, but like that you can think. Okay, so yeah, like the k value you calculate it and you will get as 0.625, right? So now let's basically plot our root locus. So everything we know. Okay, breakaway point and my centroid are same. So basically so I can delete this one, right? This is our wrong use. This will be something like this, and let's say this will be something like this, right? This is a, now as I don't have complex conjugate poles, I can skip that step, right? And the crossover point, I can see it's omega is 0 only. Okay, so yeah, I will still do it, but like you can see, right, crossover point will still be omega equals to 0, right? So this root locus will look something like this, and what I can do is I can add different colors over here, if I may. No, can I? Okay, so this will go over here and this will go over here. Okay, so and this will terminate to here, right? So like we can understand all of this. So yeah, this will be something like a infinity that we'll do. So first, like step 4 you can skip, right? Step 5 you can skip. Step 5, like we don't have any complex conjugate poles. Poles slash zeros. We don't have any complex conjugate poles slash zeros. Okay, so that we don't have, right? That we don't have. Now we can skip this one. Now coming to the crossover point. Right? Coming to the crossover point. So what is my crossover point basically? So my crossover point, if you solve that equation, right? If you solve that equation, what you will get is like two values. You have to put s equals to g omega, and like you have to like ignore one and take the another one. So one solution what you will get. Okay, I will give you this homework. Okay, I will not solve it because that will again take waste so much time, because I've already solved it in the previous example. Okay, that I have already done. So one you will get omega equals to plus minus root 5. No, you will not get, actually, sorry. Why? Because there it will be minus k. Okay, so I have to solve it again. So yeah, this is a pain in the ass. So yeah, sorry for that language. Okay, so we have to solve this one, right? This will be difficult, but still this will take time. Okay, so what I will do is, like, you have to do some work. Okay, I've already solved for the first example. Okay, like this one only. So you solve this, okay, and say what is the answer. Okay, say what is the answer. Like the answer I'm already saying is that, like, you have to reject the one of the solution that will be like that will come out to be omega imaginary, and the other one will come out to be omega equals to 0. So you will pick that solution. Omega can't be imaginary, right? It can't be imaginary. Okay, it has to be something real. Okay, so yeah, but like after end of this lecture I will complete the answer, right? I will write down the answer and complete it. Okay, so I'm just not wasting your time. Okay, you'll get two solutions and you will ignore the other ones, and you will just take the omega equals 0. Like from here also you can understand that my crossover point is 0, right? My crossover point is 0. Okay, so yeah, the other two solutions you will ignore because you will get your value of k as negative. Okay, so yeah, I hope you got the concept. So from here I will not write. Okay, I will not write, but the crossover point that you will get is omega equals to 0. Okay, so if I copy this one, right, and like I got the final okay, too many pages, I have got the final root locus basically. Okay, this is for k greater than 0 and when I have positive feedback, right? When I have positive feedback. Okay, so basically let me mark the directions. So this is my direction and this is my direction, this is my direction, and this is my direction, right? So these are my directions, and this is like coming from here and this is coming from here, right? So these are my direction of root locus, and like this point is k tending to infinity and this point is k tending to infinity, right? And this point is k tending to infinity. Okay, and this point is also k tending to infinity, right? So all of these are k tending to infinity, and here, right, I'm starting from 0, right? K equals to 0, I'm starting k equals to 0, k equals to 0, and k equals to 0, and this is my break away point. And what is the value of k here? K is 0.5625, right? So if I write the value of k, it was k break equals to 0.5625. okay, let me just recheck what did I write down over there. It was, yeah, 0.5625. yeah, so this will be the value of k. Sorry for going fast, okay, because like I've already solved everything, so I don't want to waste your time, right? You can do it by yourself because already solved this example, just k becomes minus k. Okay, so that you have to understand, right? So yeah, so what do I see in the other case, right? Like in the actual case, why did I solve in the first time, right? So this was the root locus came like this, where my k was positive and I had negative feedback. Here my k is positive but I have positive feedback. So what is the difference you see? Like between here it lied but here it didn't, right? Here it didn't. Okay, so yeah, everything will be complementary. Like in the real axis everything will be exact complementary, if you can understand. This is going to minus infinity, this is going to plus infinity, but here, right, they are all finite. Okay, and one more thing, like this is also unstable and this is also unstable. Okay, why did it go? Like both of them are unstable, but this is, like, I can say positive feedback makes it more unstable. Okay, that I can say. Okay, so yeah, this is the difference. I hope you can understand, right? What is complementary root locus, what is root locus? Like everything is same only, just the rule has changed, hence that's why it is complement, right? Real axis is total complement of this one. Okay, so yeah, this was it for this question. So let's now start another question. Okay, this one also I will go a bit fast. What is the main concept? The main concept is angle of arrival and like angle of, for this set it is angle of departure. Okay, angle of departure I have to find using that new formula. That's why I took this question. Again, the same question, right? I hope you remember this was the third root locus that we plotted during the start of this chapter, right? So yeah, let's start this question basically. So like first again, right, we have to find the open loop zeros and the open loop poles. So where are my open loop zeros? So my open loop zeros, right, again you find the roots of this equation. Okay, it is minus b plus minus b square minus 4ac, which is 8 divided by 2a, right? So which is 1 plus minus basically j, right? It is basically minus 4, so it's j2. Okay, minus 4 under root, it is j2, and 2 divided by 2 is j1, right? So it is 1 plus minus j, right? 1 plus minus j. Okay, so these are my complex pole, hence I will get like concept of angle of departure, right? Concept of angle of departure. So now where are my open loop zeros? It is s equals to minus 3. It is s equals to minus 3 basically. Okay, so here are my open loop zeros, right? So if here are my open loop zeros, so my pole will be simply like I have two poles and my zeros are 1. So like my branches will be 2 itself. I will have 2 root locus branches, and how many poles I will have, how many asymptotes I will have, or virtual zeros, like z virtual I will have as p minus z equals to 1 itself, right? 2 minus 1 equals to 1 itself. So this will be my z virtual basically. This will be my z virtual. Okay, so like I have already like plotted this one up, okay, just to save time. So these are my complex conjugate poles, and this is my zero, and I will have another virtual zero. Now you tell me, you guess where will it lie? So basically, right, so I can't, like my test point can't lie over here. That is my second what do you say, second step, right? My test point can't lie on this here, because I will have always odd number of zero or poles in the right hand side of my test point, right? Which is not the rule for my complementary root locus, as you can see, right? Okay, sorry, I have made one mistake. I've forgotten to put the block diagram here. So without that, you won't be able to understand whether this is a complementary or normal root locus. So if they haven't told us anything, right, what you will think is normal root locus, right? Normal root locus. But it was my mistake. Like this is question for complementary root locus, so I have to copy this block diagram and put it over there. So if nothing is mentioned, right, if nothing is mentioned, generally they will mention, right? If nothing is mentioned about the feedback, or they haven't given the block diagram, they have just given the OLTF, always consider it as negative feedback, okay? Because nothing is mentioned, and by default 95% of the cases negative feedback comes, right? So that's why you think like that. Okay, but here, like this question was meant to be positive feedback. Due to my negligence, I'm really sorry, like too much work. So that's why I forgot to put this block diagram here, right? So yeah, you put this block diagram here, and from here you can understand that this is a positive feedback, and this is a question of complementary root locus, right? This is a question of complementary root locus. So here, right, as this is a positive feedback, like my test points will lie around here and not around here. Okay, so as I need odd or zero number of poles and zeros on the right hand side. So what you can see is on the right hand side, like these two are even, right? You can say these two are even, or here also 0, right? So around this point, this will always lie on my root locus. This will always lie on my root locus, right? On the right hand side will always lie on the root locus. Okay, so yeah, this is true. Now what about my like what is the range of my test point? So can you write me the range of the test point? So the range of the test point is basically between from -3 to infinity. Okay, the range of the test point is from -3 to infinity. So this is the range of my test point. Now let's go to the step 3, the angle of asymptote. So here, right, we only have one asymptote, and you can blatantly see that it is 0, right? So still it's a procedure. So theta asymptote is basically 360 handwriting is going bad. Divided by p minus z into k, right? So it is p minus z into k, but k is going from 0, 1 and p minus z minus 1, right? Okay, so this is going like this, so this will be 0 only, right? Because you can make k equals to 0. If you make k equals 0, like only I have one right, one asymptote, so I will only start with k equals 0 and this will go to 0. Basically on the positive x-axis my asymptote is that I already did, right? You can, like, the question is almost finished. Okay, just have to find the angle of arrival angle of departure for these two poles and the question is finished. Okay, there is no concept of centroid because my asymptote, I have only one asymptote and that is on the real axis, so no concept of centroid. Okay, so like the previous that first question only. Okay, like the question that was used to solve this using the normal root locus method, that only. So what about my breakaway points or breaking points? So here, right, I have two zeros, like this is a virtual zero but still I have two zeros, so I won't have a breakaway point but I will have a break in point, right? Break in point. Two branches will come together. Okay, they will again meet up, patch up, and then they will break in and then they will go to their respective zeros, right? So terminate to their respective zeros. So I won't have breakaway point because I don't have two adjacent poles, but I will have break in point, right? I will have break in point basically. So now what I can write, what is my OLT, right? What is my OLT? The solutions again, right, will be same. The solutions again will be same. Here I will still solve, right? So this is my OLT basically. So what I can write here is 1 minus k s plus 3. This is the characteristics equation, right? Equals to 0. So this is my characteristics equation. Now what is my A of s? What is my A of s? A of s is s plus 3. What is my B of s? B of s is s square minus 2s plus 2, right? B of s is this, and A dash of s. What is A dash of s? It is 1. And what is B dash of s? It is 2s minus 2. Okay, so again, right, we have to solve that equation, which is A of s and B dash of s minus A dash of s into B of s, which is equals to 0, right? And this, right, my s equals to s test point should satisfy this equation, right? Or like not test point, you can say my break in point, right? This should satisfy my equation. Now I will get two solutions from here, and one I will have to reject and one I'll have to take, right? One I have to take. So I've already solved this one. Okay, won't waste time, so you try to solve it for yourself. So I will get two solutions. One will be SB1, okay, one will be SB2. So what I can write is, what is my SB1? SB1 is minus 7.12, and what is my SB2? SB2 is basically what was it? It was 1.12. okay, so my SB2 was 1.12. so like now which one should I pick and which one should I leave, right? So let's come back and again copy this range, and from here only we can understand, as my breakaway or break-in point will always lie on the real axis, okay, and it has to satisfy like this range, right? My test point should always lie in this range, that I know. So this, right, this isn't satisfying. Okay, this is not lying in this range. Like my test point should lie between -3 to infinity. This is -7. okay, so no, this isn't lying in this range, but this is, right, this is lying in this range, right? this is lying in this range. So if this is lying in this range, so what is the value of my k? What is the value of my k here? Like if you find, right, so here in the same question in with negative feedback, you would have seen that the k value was plus 16.24. Here, right, what will happen, the k value will just change its sign. Okay, as I mentioned, right, k right now is not equals to minus b upon a, k is equals to plus b upon a, as mentioned in the previous lecture also. So k, right, for this particular value, k will become minus 16.24. okay, k will become minus 16.24, and for this, the second breakpoint, my k will become, k will simply become 0.246, right? My k will simply become 0.246. So yeah, it is positive. So this is valid breaking point. Okay, so I hope you understood that. So let me copy this one. Like this point is plus 1 only, right? This point is plus 1 only. Okay, so here, yeah, no need to write plus 1, just 1 is good enough. So like what I can say is this is plus 1, so my break-in point will come something like this, right? They will come something like this. From poles, they will come something like this. So from here also I can get a basic intuition, basic idea of what is my angle of departure, right, from each of these poles. It will be something like this. Okay, it can't be something like this. Okay, it can't be something like this. Generally it doesn't happen. Okay, it can't be something like this. It is coming something like this. So if it's something like this, it should be like for this, right, for this P1, let's say it should be between 0 to minus 90 this time. Why? Because this is in the downward direction or in the fourth quadrant. Quadrant is like this, right? And I'm going downward direction. Y is in the negative, right? Y negative. So y is negative, x is positive. So this will be negative angle. So this will lie between 0 to minus 90. Okay. So yeah, this is this one, right? So like I can see my break-in point here, right? Is break-in. Is breaking equals to 1.1. okay, so this is my break-in point basically. Now what about my angle of departure, right? Let's straight come back to my angle of departure. So like I've already written it down, the formula, right here, right? What is the difference? Difference is I have 0. okay, I don't have any more 180. That angle condition has changed right now, so it is 0 right now. So just that thing you have to keep in mind. All the other calculations are the same, right? So for here, for departure, right, we subtract the poles, right? We subtract the poles. Like I hope you remember, right? So that's how I told you to remember. So we are calculating it for poles, right? We're calculating the departure for poles, so we'll subtract the other angle of poles, right? And if I want to calculate for angle of arrival, what I will do is I will subtract the angle of zeros. Okay, this won't be subtraction, this will be plus, sorry, this will be plus only. Okay, so I will subtract the zeros and I will add the poles. Okay, so yeah, there's this one. So now right now let's basically compute. So like what will be my theta departure, right? Theta departure, and let me copy the pole first, like this one first. Okay, and let me name this one as P1. So let me name this one as P1, right? So this is, let's say this is P1, this is P2, and this is Z itself. So I want to calculate the angle of departure for P1. So what is the angle of departure for P1? So it is basically summation of theta Z minus summation of theta P, right? Okay, so this is basically my formula. So what is my theta Z? What is my theta Z? This is 1, right? This is 1. Okay, so for theta Z again, right, I will use that same thing, that I will draw a vector from here to here. Now I will write what is my x distance. X distance is 4, right? Okay, I will not write it like this one, I will write it like this one. x distance is 4, and what is my y distance? Basically y is 1 itself, right? Y is 1. So like we have already calculated this formula, like the summation of all this will be same. Okay, just I have removed that 180, everything else will be same, just I have removed that extra 180 term, right? So yeah, this calculation will be same only, still I'm doing it. So this is 1 and this is 4, that's why I'm doing it a bit fast, right? So this already we already know all this. This is 4. So what is my theta z? Basically theta z will be, as one thing to mention here is, okay, this is positive and this is also positive, so the theta z this time will be positive, right? So like my x distance is positive and my y is positive, so first quadrant, so it is positive only. So it is tan inverse y upon x. So y is 1 upon 4, and like I hope, like I've written it down, you remember also that it comes out to be something like 14 degrees, something like 14 degrees, right? So yeah, this comes out to be this. Now let's calculate the theta p basically. So I will calculate theta p2, because p1 is the pole itself for which I am calculating the angle of departure, right? So if you see, right, if you see that I am just moving upward direction, right, my x distance is 0 for this p1 and my y is finite, okay, it is 2, right? 2. So 2 upon 0 is, so tan inverse 2 upon 0, okay, equals to 90 degrees. Okay, tan inverse 2 upon 0 equals to 90 degrees, right? So this is what my this theta p2 is. So if theta p2 is this one, so what is my angle of departure for p1? It is simply equals to 14. Okay, pole will be get subtracted, right? 0 will get added and pole will get subtracted. So 14 minus 90. Okay, so it is simply equals to 76, right? It is simply equals to 76 and with a minus sign, just be careful. So that relation will still follow, right? That my theta departure for the pole p2 will be just negation of this one, will be just opposite of this one. So theta departure p2 will be 76 degrees. Okay, so theta departure p2 will be 76 degrees. Now I'm almost like completed with my root locus. Just what is left? Just the crossover point is left, right? So let's see if we can compute the crossover point. So here, right, again I will write down here, but I will give you the homework. Okay, like from here also you can understand that if it is like 65 minus 76 and this is minus 76, so obviously I won't cross over my root locus in the imaginary conjugate pair, right? I will cross over here only. I can see, right, it is crossing over at omega equals 0, that I can already see. Okay, so it won't cross over like this one. Okay, because if I have one crossover point here, I need another crossover point here. Okay, they will be conjugate, but I can only have two branches, right? Two branches I can only have, right? So here again I have to choose another, like this is already taken one of the roots, so I can have only one root. Okay, hence my omega equals to 0 is a crossover point. Okay, so like this intuition you can understand. Intuition I gave you, calculation you do. Okay, I will write down the calculation in the like notes. Okay, don't worry, but intuition I gave you, right? Okay, so omega equals to 0. Now if you put omega equals to 0, what is the value of k basically? So if you put omega equals to 0, right? Okay, where is my this characteristic equation? Where did it go? This is gone. Okay, here, right? You put omega equals to 0, so you get your k as 2 by 3, right? Okay, 2 by 3, so it is simply equals to 0.667. okay, so k is positive, which is fine. Okay, so yeah, this one is for this crossover point, and I have already plotted this one, right? So you can see that my angle here is minus 76 in the clockwise direction, in the downward direction, hence this is 76, but this is actually minus 76, and this is 76 in the anti-clockwise direction, so this is plus 76, right? So I hope you understand, and these are the directions. So this is the direction and this is another direction. Okay, so this question I took just to calculate the angle of arrival, right, for what do you say, complementary root locus. Just the difference is we don't add 180 anymore, we just simply do the angle calculation and subtract them, right? So yeah, that is the difference, and everything else is very simple, like this ending at k equals to infinity, and this is like this is also ending at k equals to infinity. This is also ending at k equals to infinity, right? So both of them are ending at k equals to infinity, and like yeah, this is k equals to 0.67, right? And this is k equals to 0, and this is k equals to 0. So these are starting from k equals to 0, originating from k equals to 0 with angle 76, right? And then they are breaking in at s equals to 1.12, right? This is a valid breaking point, and then, right, what is happening? They are going away again. So this is terminating here at 0 minus 3, and this is terminating at a versus 0 with the axis 0 degree, right? So I hope you understand. So you can see the difference of the k greater than 0 negative feedback. That is the case which I solved earlier, right? So everything you can see, right, it is totally complementary. The real axis is totally complementary, and here I have a breaking point, and there I didn't have a breaking point. There I had a breaking point here, right? The other point that I choose, right, that I rejected now was chosen there, okay, and the point that was rejected here was chosen here, right? Okay, so that is basically the complementary root locus. You choose some and you reject some, right? So basically in your life also you choose some and you reject some. So that is what you do, right? So yeah, so I hope you got the basic understanding, the differences between the root locus and complementary root locus, and I hope you're understanding, right, the links you're finding out, right? What is the link between the root locus and the complementary root locus? This is nothing different, similar thing only, just we choose different things, right? Because the angle condition has changed. That is the only difference. Angle condition of what? The OLTF for my test point to lie on the root locus, right? What is root locus? Root locus is the locus of my closed loop poles. So everything, right? This is also closed loop poles, this is also closed loop poles with a variation of my k. Okay, very important, with the variation of my k. So now let's go to the case 2. So what is my case 2? My case 2 is when my k is less than equals to 0. So if my k is less than equals to 0, basically my k is negative. K is negative. So if my k is negative, so with negative feedback, if my k is negative, this is the standard format of OLTF, my closed loop characteristics equation will effectively look like positive feedback. Okay, so my closed loop characteristics equation effectively look like positive feedback, right? Positive feedback. So my like the closed loop characteristic equation will effectively look like positive feedback. Why? We will see, right? So basically, like, what is my characteristic equation? So my characteristic equation is like this is with negative feedback, right? Negative feedback, hence my characteristic equation will be 1 plus g of s into h of s equals to 0, which is with negative feedback. Okay, which is with negative feedback, right? So this is what my characteristics equation is. So what I will do is like I will write this g h of s in this format. Okay, replace this one, okay, not this one. With this one, so this is simply 1 plus this equals to 0, right? So this is equals to 0. So now this is my equation 1. Let's name this equation 1 and let do one thing. What should I do is let my k, I will name new variable k hat, which is equals to minus of k. Why? We'll just see in a second. Okay, we'll just see in a second. So what does my k is equals to? K is equals to my k hat, right? K is equals to my k hat. So now, like, if my k is going from 0 to what? 0 to minus infinity, right? K is negative, so it is going from 0 to minus infinity. Then where will my k hat travel? So k hat will travel from 0 to plus infinity. So is this something familiar? So we know, right? We know the traveling of 0 to infinity. Okay, in the previous cases we already solved, right? Case 1 we solved, so that is what I am simply converting to basically convert to case 1, and for those we know the rules for positive and negative feedback. So that rules we will follow here, right? We will not follow any new rules, right? So my equation 1, equation 1 becomes basically, it becomes like I will replace my k with, sorry, this is minus k, this is minus k, sorry, really sorry, minus k. I know you were screaming, sir, this is minus k, what are you doing, minus k. Okay, so I will replace my k with minus k hat, right? In this equation 1, I will replace my k with minus k hat, minus, it will be same only, all the other things will be same only, right? Okay, so other things are same only, which is equals to 0. Now is this equation looking something familiar to you? Why did I tell you at the starting itself my closed loop equation will effectively look like positive? So here I have a negative sign, and this k, right, this k hat is always positive. So this is like effectively a positive system, positive feedback, but this is in reality not a positive feedback. In reality this is negative feedback. Okay, but we will assume, like, we'll think of it like a positive feedback, and we'll solve the root locus like that. Okay, so yeah, this is effectively positive feedback, but in actuality this is not a positive feedback. So it is important, right? It is in actual, like in implementation, real implementation, this is not positive feedback, but effectively we can think of it like a positive feedback and follow the same step for CRL, right? Complementary root locus. Follow the same step for CRL, put k hat, the ranges of k hat, and then change k hat to minus k. Okay, and then you solve it like this. Okay, so just the k values will change this time. The k values will change. K value has to be always satisfied negative, right? K value will be always here negative. So that you have to keep in mind. Okay, follow steps of CRL. Okay, okay, just the k value will change, everything else will remain same. Like for k hat is going from 0 to infinity, right? So everything will be same. Just when I will replace my k to k minus, when I will replace my k hat to minus k, then the limits will change. My k hat was going from 0 to infinity, now it will go from 0 to minus infinity. That is all that will change, right? K from positive will become negative, right? Because it has to terminate to a virtual 0 or something. So yeah, this was the case 2a, right? Now what about the case 2b with positive feedback? So basically with positive feedback, what will happen? Effectively my system will become negative feedback, right? Why? So again, right, I will just copy the characteristic equation. Okay, this one I will copy. Okay, and this time this is not k hat, this is actual k, right? This is actual k, because I have positive feedback here, and if I have positive feedback here, then this sign becomes negative. Okay, and this is k, right? Now again I will do the same thing. I can just copy and paste. I can just simply copy and paste, right? Okay, I'm sorry, but I will just save time, right? I'll save time. So I'll just copy and paste over here. Okay, So we paste, right? So effectively if I replace, right, again k hat to minus k, so k will become minus k hat, and if my k goes from 0 to minus infinity, k hat will go from 0 to infinity. That you understood, right? Now what does my equation 2 become? What does my equation 2 become? What does my equation 2 become? So equation 2, instead of minus this time, becomes plus, right? Plus, okay, because I already had a minus over here and I replaced with minus k hat, this become plus, right? This become plus. So if this becomes plus, so what is this equation looks like for what is the characteristic equation for this type of system, right? 1 plus. So it is basically effectively a negative, but in real implementation this is a positive feedback, but effectively we can think of it like a negative feedback. Okay, effectively we can think of it like a negative feedback. And basically what steps we follow? We'll follow for normal root locus. Whatever steps we did, right, we'll just follow those steps, right? We'll obviously not follow complementary root locus, as this is negative feedback and this k hat is positive. Just at the end stage we'll replace k hat with minus k, and there the values of k will just become opposite. Whatever values you found out on the root locus, you just put a minus sign ahead of that, and that will be your answer, right? That will be your answer for this question. That you have to make the change, right? That only you have to make the change. So here, right, I have written down the confusion matrix. So this is like a confusion matrix, known as this kind of format is known as confusion matrix, or you can say truth table, right? Truth table you can also say when like this is true and this is also true, then this is followed. When let's say this is true but this is not true, this is true, so this one will be followed, and like that, vice versa, right? So what I can see, if my k is positive and I have a negative feedback, the simplest solution is normal root locus, right? You solve it using normal root locus. Now if my k is positive but I have a positive feedback, then how you solve? You solve by the rules of complementary root locus. Okay, you solve by the rules of complementary root locus as taught to you in the previous lecture as well. Now if my k is negative, now things become bit tricky. If my k is negative, so I have to use complementary root locus for negative feedback. Why? Because due to negative k, this negative feedback changes to positive feedback. So what I can write is negative, okay, my handwriting is not that, negative value of k, basically changes the type of feedback effectively. Okay, but like originally it is that type of feedback only. How can it change the feedback type? But effectively what we can understand, that if my value of k is negative, then it changes the type of feedback, right? From like this is basically becomes a positive feedback instead of negative feedback. That's why we're solving using the rule of complementary root locus, as this k is negative and this positive feedback becomes negative feedback as I am solving, like I would solve using root locus, right? Okay, so yeah, I hope you got a brief overview of this lecture, and like the homework I will put. So you have to do few hard work also. Only I will not solve, right? You have to do along with me. Sit in the chair and solve along with me, right? So yeah, I will write all the solutions, and yeah, I'll send it to the notes, and yeah, see you in the next lecture basically.